Hello, calculus students and general seekers of truth. Now we will look at an example here of finding a power series for this particular function and also its interval of convergence. And one of the main ideas here is to try and get this function, get this expression here, to look like, try to get this to resemble 1 over 1 minus r. Because if we can do that, then we know for a fact that this must be equal to the summation of n equals 0 to infinity of a, which is the first term, which is just 1, r to the nth. Okay, so we want to get this to resemble that somehow. And the way to rewrite this is not too difficult. We could take this series here, or sorry, this function here, 1 over 1 plus x squared, and say that, well, it's really equal to 1 over 1 minus negative x squared. Okay. So in fact, r here is equal to negative x squared. And so now it's not too difficult to expand. This just becomes the sum of, from n equals 0 to infinity of r. So this right here is like our r value. So negative x squared to the nth. Okay. And if we want to write out a few terms, that's not too difficult to do either. When n is equal to 0, this thing is just 1 plus, when n is equal to 1, this is just negative x squared. The next term after that, when n is equal to 2, this is positive x to the 4th. When n is equal to 3, you get negative x to the 6th, and so on. Okay. And the interval of convergence is, again, not too difficult to find. The interval of convergence is really like asking, you know, when is it that this value here, that's r, is going to be less than or equal to 0, in absolute value. Less than or equal to 1, I'm sorry. Take the absolute value away, you get that x squared has to be less than 1, so this is just another way of saying that x has to be between 1 and negative 1. Okay. At the endpoints, this will not be true, so we can leave it right here as strictly less than or greater than. Okay, so there we go. Nice example here of manipulation of a power series. Alrighty, so now I'm going to take a bigger leap forward and say, let's find a series of some sort that will approximate the tangent inverse function. Now, I welcome you to explore and try on your own to use the Maclaurin or the Taylor series to find the tangent inverse function. You can do it, but it will get quite complicated quite fast. Oops, I forgot to mention one thing in this problem. This should say centered at x equals 0. And if we go about this by finding the Maclaurin series for this tan inverse function, I think it can be done, but it gets quite complicated and quite messy very, very fast. Okay, so we can take a different approach by using integration and differentiation, two basic concepts of calculus. Integrate something and take the derivative of it. So if you recall, the derivative of the tangent inverse function is equal to 1 over 1 plus x squared. Okay. Now, gee, this seems very familiar. This is in fact equal to the series that we just developed up here. 1 over 1 plus x squared is nothing more than this series. So we can say that this is in fact equal to the sum of, from n equals 0 to infinity, of negative x squared to the nth. And we can expand this out, which is 1 minus x squared plus x to the 4th minus x to the 6th, and so on, onwards to infinity. Well, if we want to then go from the derivative back to the original function, we can just take the antiderivative of everything. Okay, so the tangent inverse function then must be equal to the antiderivative of all of this stuff. The antiderivative of the derivative, but that's like taking the antiderivative of this, and the antiderivative of this series, and the antiderivative of this polynomial expansion. These are all the same thing, and we're taking the derivative with respect to x. This is the antiderivative with respect to x. So this should all have like a dx in here somewhere. Okay. And I'm going to write dx in the front here, since technically this series goes on forever, so I can't really get to the end to write dx. So the tangent inverse function then is equal to the antiderivative of all this of this expression, which is the antiderivative of this. And finding the antiderivative of all this stuff here is maybe a little bit complicated. So I'm going to use the antiderivative of this polynomial here. So the antiderivative of this expression is easy to find. It is just x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 onwards forever. But let us not forget that when you take the antiderivative, you also have a constant here. So I'm going to write the constant in front. Now to solve for the constant, we know that when x equals 0, the tangent inverse of x, or the tangent inverse of 0 here, is equal to 0. Okay, so when x, I shouldn't really need to write this part. Basically, the tangent inverse function from a graph, previously looks kind of like this. It goes through the origin. So when x is equal to 0, the tangent inverse is also equal to 0. So 0 equals c plus it, all that stuff here is 0, since you're plugging in 0 for x. So that means c is equal to 0. So we can say that the tan inverse is in fact equal to this expression, x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7th. And we have to be very careful here, again, regarding our interval of convergence. Where does this really converge? So I'm going to try and write out the general term for this power series. Notice that it alternates between positive and negative. So this is this trick of using -1. I'm starting here at n equals 1 because there's no constant term. The first term in this series is x, so we want the first term here to have a power of 1. And then if you look at the pattern here, it's just the odd powers over that odd number. So this is x to the 2n minus 1. It's important that we use 2n minus 1 here instead of 2n plus 1 because, again, we're starting at n equals 1. Okay? All of this over 2n minus 1. And now the question is, well, where does this series converge? So we can use the ratio test. So we take the n plus 1 term over the nth term, which is equal to, we can get rid of this -1, so this is x to the 2n over 2n times 2n minus 1 over x to the 2n minus 1 in absolute value. This all reduces down to, and if we take the limit of all this as n approaches infinity, we end up with the limit as n approaches infinity of, what do I have left here? I have x on the top times 2n minus 1 and just 2n in the denominator. So the leading terms here is going to go down to 1, so this is just going to be equal to the absolute value of x. So it will converge when the absolute value of x is less than 1. So the interval of convergence is between positive 1 and negative 1. Okay. Now, in this case, this is not really, this is not strictly a geometric series anymore, because you have some other terms, of n in here. So we do have to check the endpoints. Alright, so I'll leave that to you to kind of work it out on your own, but you can see that if you put 1 or negative 1 into here, you get an alternating series that does converge. So this is true if we put to put the equality sign in there, and it's a good exercise for you to work that out on your own, just to see that in fact is an alternating series if you were to put negative 1 or positive 1 in there. So what this says is something very nifty and useful for us, which is if we want to estimate the value of the arctan function or the tangent inverse function, again, this function is going to yield many irrational answers, many transcendental answers for which we don't really know what the exact answer is. So the best way to approximate it is actually to use this series right here, which is a type of which is derived from a power series. Okay. And you'll see some other examples here, and as well as in your homework exercises, that ask you to find a series approximation for a function that may be difficult to find the exact values for. The main part in here, the main caveat, of course, is that we have to look at any sort of interval of convergence. So arctan, or the tan inverse function, is equal to this infinitely long polynomial only if x is between 1 and negative 1. Now you might say this is a small interval, why bother? But if you look at the tan inverse function, between negative 1 and 1 is where most of the action happens, where most of it changes. As you extend out further, this function is going to level off at pi over 2 and negative pi over 2. So for very large values, we know that arctan is going to approach pi over 2 and negative pi over 2. It's really this zone here in the middle between negative 1 and 1, that's where the values change maybe more rapidly, and we have a way to approximate what the values actually are. So there we go, an example of the use of a power series. I will end this here. Thank you for watching, and have a wonderful day.